Have you ever wondered how we can describe something, well, messy, with something as clean and perfect as mathematics? You look at a jagged sound wave on a computer and it seems chaotic, but it turns out there's this secret, almost infinite recipe that lets us build any repeating pattern you can imagine, no matter how complex it looks. And it all starts with one of the simplest, smoothest shapes in the universe. So let's start with a puzzle that sounds, frankly, impossible. How on earth can you build something with sharp, 90-degree corners, like a square wave, using only the motion of something perfectly smooth, like a point spinning on a circle? I mean, that sounds like trying to build a brick wall out of soap bubbles, right? But stick with me, because by the end of this, you're going to see exactly how it's done. To solve this puzzle, we've got to hop in a time machine and go back to the early 1800s. We're going to meet a French mathematician who, believe it or not, wasn't trying to build square waves. He was trying to figure out something way more practical, how heat flows through a metal bar. And in doing that, he accidentally discovered a universal language for describing almost any repeating pattern in the cosmos. Okay, so picture this. It's 1822. The mathematician is Joseph Fourier, and he is stuck on the problem of heat. He needs a way to write down mathematically how the temperature in an object changes. And he noticed the patterns were complex, but they repeated. This led him to a totally game-changing idea. What if any repeating pattern, no matter how weird or complicated, is really just a bunch of simpler, more basic waves all added together?
Now, the official math term for these repeating patterns is a periodic function. It sounds fancy, but all it means is that you have a shape that just copies and pastes itself over and over again. The length of that repeating chunk is what we call the period, t. So think about the sound wave from a violin, the ticking of a clock, or, even our jagged square wave. They're all periodic functions, and they're exactly what Fourier's big idea was all about.
So Fourier had this amazing insight, but an idea isn't that useful until you can turn it into a tool, and that's exactly what he did. He created what we now call the Fourier series, and honestly, the best way to get your head around it is to think of it as an infinite mathematical recipe. And here it is. This is the recipe. On the left side, that f of x, that's our final dish. It's the complex wave we want to create. And on the right, that's our list of ingredients. It's an infinite list, but the ingredients are super simple, just basic sine and cosine waves. The recipe says that if we add up just the right amount of each of these simple waves, we can perfectly build any repeating shape we want. And this recipe idea is so important. We're not just getting close to the shape, we are perfectly breaking it down into its most fundamental parts, or frequencies. It's like a master chef who knows the exact amount of flour, sugar, and eggs for a perfect cake. Fourier's method gives us the exact amount of each sine and cosine wave we need. So the big question is, how do we know how much of each ingredient to throw in the mix? That's where these things, the coefficients an and bn, come in. Now, don't get scared by the calculus here. You don't need to solve it. Just think of these integrals as a kind of magic measuring cup. They measure exactly how much cosinus and sinus of a certain frequency is hiding inside our original shape. They tell us the perfect strength for every single ingredient. And how do those magic measuring cups work? Well, the secret sauce behind it is a deep mathematical property called orthogonality. The best analogy is a prism. You know how a prism takes white light and splits it into all its different colors? Well, orthogonality does the exact same thing for waves. It lets us pull the mixture apart and isolate each individual sine and cosine wave so we can measure it all by itself. Pretty cool, right? Okay, so we have a recipe that can describe any repeating shape that's just sitting there. That's already amazing. But the universe doesn't just sit still, does it? It's always moving, always changing. So the next big question is, can we use the same recipe to describe not just a shape, but a whole system that's evolving over time, following the laws of physics? To do that, we need an even bigger tool. It's called a partial differential equation, or PDE for short. All a PDE is, really, is an equation that describes how something changes, not just over time, but across space as well. The best way to think of a PDE is as the rule book for a physical system. It doesn't tell you what the system looks like right now, but it lays down the ironclad laws that govern how it has to behave. And these aren't just some abstract toys for mathematicians. PDEs are literally everywhere. The heat equation, that's the one Fourier was working on. The wave equation, that describes everything from a vibrating guitar string to the ripples spreading in a pond. They really are the fundamental language of change in our universe. So now we've got two huge ideas on the table. We have the Fourier series, our recipe for building any shape, and we have PDEs, the rulebook for how things change. Now, on their own, each of these is brilliant, but when you put them together, that's when the real magic happens. They form one of the most powerful partnerships in all of science.
But here's the problem. We have the rulebook, the PDE, but how do we actually find a solution that follows all the rules? Like, how do we find the exact shape of a vibrating guitar string at any given second and be absolutely sure that its movement is perfectly obeying the laws of the wave equation? It's a tough problem.
And the answer, in a moment of true mathematical beauty, is that we use the exact same tool we started with. We use Fourier's infinite recipe. This is how the partnership works, and it's so elegant. The PDE sets the rules of the game. The Fourier series gives us a massive box of Lego bricks, our simple sines and cosines. So what we do is we test each individual brick to see if it obeys the rules. Then we just build our final solution using only the bricks that we know are rule-abiding. It's a genius way to guarantee our final answer is correct. Now, this partnership isn't just a neat trick. It lets us solve incredibly complex real-world problems. But sometimes it does something even stranger. It reveals these deep, surprising connections within mathematics itself. Let me show you one of the most famous examples. It's a real mind-bender. Okay, let's take a shape we all know from school, a simple parabola, y equals x squared. Now you might be thinking, wait, that doesn't repeat. And you're right, it doesn't. But what if we just chop out one piece of it? And then we just copy and paste that piece over and over and over again. Boom, now we've got a periodic function. And if we have a periodic function, we can write a Fourier recipe for it. So we do it. We run our repeating parabola shape through the Fourier recipe. We calculate all the ingredients, all the coefficients, and what we get out is an infinite series of numbers. But here is where it gets absolutely wild. By plugging in a specific number into our series, we can use it to find the answer to a completely different and very famous mathematical problem. And this is the jaw-dropping result. This famous puzzle, called the Basel problem, asks a simple question. What do you get if you add up the reciprocals of all the perfect squares forever? For centuries, the greatest mathematicians on Earth knew this sum added up to a specific number, but they had no idea what it was. And it turns out by applying Fourier's recipe to a simple parabola, you can prove with absolute certainty that the answer is pi squared divided by 6, a bizarre, beautiful connection between waves, parabolas, and one of the most fundamental numbers in the universe. And that's really the big takeaway here. Fourier's method is so much more than just a tool for physics or engineering. It's like we've discovered a deep truth about how numbers and functions are structured. It's a language that doesn't just describe the world we see around us, it reveals these hidden, secret pathways within the abstract world of pure math. Which, of course, leaves us with one final big thought. We've seen how this language of waves lets us build jagged shapes from smooth circles, and even solve ancient problems about infinite sums. It just makes you wonder, what other profound secrets about our universe are sitting there, hidden in plain sight, just waiting for us to discover the right language to describe them?